We look up at the stars, day after day, decade after decade. We send out signals. We build telescopes. We imagine, and yet nothing looks back. This silence is not just the absence of sound. It's a presence, a question, a mystery, a mirror. If our solar system is ordinary, and it very likely is then somewhere among the hundreds of billions of stars in the Milky Way, life should be stirring, life should be speaking, but it isn't. Why? This question, simple and sharp, was once asked at a lunch table in Los Alamos. It wasn't posed by an astronomer or a ufologist. It came from a physicist named Enrico Fermi. The conversation started with a cartoon alien stealing trash cans in New York City, and it ended with a deceptively simple question: where is everybody? Fermi didn't publish papers on alien life. He wasn't obsessed with flying saucers. But that one question stuck. Others took it and gave it weight. In 1975, an astronomer named Michael Hart built on the idea and argued that if intelligent extraterrestrial life existed anywhere in the galaxy, it should already be here. He saw no trace of visitors, no artifacts, no communications, no ships. His conclusion: they are not here. Therefore, they do not exist. He believed that any sufficiently advanced civilization, once it reached the capacity for interstellar travel, would spread system by system, planet by planet, until the entire Milky Way was colonized. That process would take only a few million years, a blink in cosmic time. And yet, we find ourselves in an unvisited corner of the galaxy. In 1980, another physicist, Frank Tipler, sharpened Hart's argument. He proposed that advanced civilizations could build self-replicating machines, artificially intelligent probes capable of reaching other star systems, using local materials to duplicate themselves, and then moving outward again, a galactic wave of intelligent machines. If that had happened, Tipler argued, we should have seen evidence. We have not. But there's a problem at the core of this line of thinking. It assumes that civilizations behave like colonists, like explorers, like conquerors, that they spread because they can. But what if they don't? Enter Frank Drake. In the early 1960s, he proposed an equation now famous which tries to estimate the number of detectable civilizations in the galaxy. His formula considers star formation rates, the number of planets per star, the fraction of planets where life arises, the fraction where intelligence evolves, and crucially, the lifespan of a communicative civilization. The equation is elegant, but its variables are filled with uncertainty. Plug in pessimistic numbers and you get near zero. Plug in optimistic ones and you get tens of thousands. The truth might be somewhere in between or nowhere close. One possible answer to the great silence is chilling. A thought experiment known as the dark forest theory. Imagine the universe as a vast, dark forest. Every civilization is a hunter, moving silently among the trees. To reveal your position is to risk destruction, for in the forest you cannot know the nature of others. You cannot know their intentions, so you stay quiet, you stay hidden, because survival depends on it. We, on the other hand, have been shouting. We've sent radio waves into the void. We've launched probes like Voyager, carrying golden records with our sounds, our languages, our maps. We've illuminated the trees. We've announced ourselves. And now we wait. Maybe someone has already seen the light. Maybe they are watching. Arthur C. Clarke once wrote, "Two possibilities exist. Either we are alone in the universe or we are not. Both are equally terrifying." He may have been right. The prospect of cosmic solitude is crushing, but so is the idea that something is out there and chooses not to answer. Perhaps they fear us, our wars, our waste, our weapons. Or perhaps they pity us. There's another possibility, that intelligent life is extraordinarily rare, not because the conditions for life are rare, but because stable. Lasting environments are. Rocky planets in habitable zones may be common, but most are young and violent, bombarded by asteroids, torn by tectonics, fried by solar flares. A narrow window exists in which life can take hold. Narrower still is the window in which intelligence can evolve. Earth has been through fire and ice, through extinction and rebirth, and somehow, against odds, life endured, intelligence bloomed, and now we build machines to search for distant minds. Yet the silence continues. It could be that intelligent life frequently arises, but doesn't last. Maybe civilizations self-destruct before they can venture outward. Nuclear war, environmental collapse, rogue artificial intelligence. There are many paths to ruin. Some scientists call this the Great Filter, the idea that at least one step between the origin of life and interstellar communication is incredibly unlikely. It could lie behind us, or it could still lie ahead. If it's behind us, we're rare, perhaps even unique. If it's ahead, we may not survive long enough to send our own probes to other stars. This question, where the filter lies, is one of the most important we can ask. It has existential weight because it holds a mirror to our future. But maybe the filter isn't universal. Maybe it's cultural. Maybe some civilizations choose stillness, quiet, reflection. Maybe they reject expansion, not out of fear, but out of wisdom. Or maybe we're early. Maybe we're among the first. That thought carries its own weight. If we are the vanguard of intelligence in the galaxy, then what we do next matters more than we can imagine. What if civilizations come and go like sparks, flaring briefly in the cosmic night? The silence may not be a warning, it may be a pattern. We might look back one day and realize that the Fermi Paradox was never a paradox at all, just a question that taught us how to listen, how to wonder, how to hope. And so we listen not just with our machines, but with our minds. What lies beyond the silence is not just a matter of science, it's a matter of identity. And perhaps a matter of destiny. Signals in the dark. The stars have always watched us, but now, for the first time, we are watching back. We scan the skies with machines so precise they can detect the faint wobble of a distant planet. We study light that left its home 1,000 years ago. We send signals into space, hoping they might someday be heard or answered. And still silence. But what if the silence is not what it seems? Our planet has only been broadcasting for a little over a century. That means our signals, radio waves, television, radar have traveled only about 100 light-years into the galaxy. That's a mere sliver of the Milky Way, like tossing a pebble into the ocean and expecting someone on the far shore to hear it splash. It's easy to imagine that the galaxy should already be saturated with signals, but even the fastest waves we can send, light itself, take time. A light-year is nearly 9.5 trillion kilometers. Our closest stellar neighbor, Proxima Centauri, is 4 light-years away. That's 4 years just to say hello, 4 more to hear a reply. Communication, in this context, becomes something else entirely. Not a conversation, but a legacy. A message in a bottle cast across millennia. Now, imagine a civilization on the other side of the galaxy. Even if they broadcasted constantly, their signal would take over 100,000 years to reach us. What if they've already spoken and we just haven't been around long enough to hear? Even within this vast scale, we remain hopeful. Our best telescopes, like the Kepler and James Webb, are not just hunting for exoplanets, but for signs of something more. Technosignatures, unnatural patterns of light, structures that dim a star in a way no planet could, the shadows of intelligence. But so far, those shadows have not appeared. For a brief moment, we thought we had found something. A star KIC 84628552, also known as Tabby's-Stun, was behaving strangely. Its brightness dipped in irregular ways. Unlike any known exoplanet transit, some speculated it might be a Dyson sphere, a theoretical structure built to harness the full energy of a star. But further study revealed a more mundane cause dust, not design. Still, the search continues. A civilization capable of building such a structure would be far beyond our own. On the Kardashev Scale, a method of measuring a civilization's technological advancement based on energy use, we haven't even reached Type 1. We're somewhere around 0.7. A Type 1 civilization can harness all the energy available on its home planet, including the full power of its atmosphere, oceans, and seismic activity. Type 2 can capture all the energy from its star. And Type 3, it would command the energy of an entire galaxy. Humans, a galaxy-spanning civilization. Their machines might drift silently through interstellar space. Their communications might ride beams of neutrinos or quantum entanglement, invisible to our crude sensors. Their presence could be as subtle as a change in background radiation, or as grand as the construction of new stars. But here's the thing, we don't know what to look for. We only know what intelligence looks like here. On Earth, we assume that intelligence out there must mirror ours in some way, but maybe it doesn't. Maybe it lives in forms we cannot comprehend. Maybe it thinks in timelines we cannot imagine. There's another idea, one that's as unsettling as it is plausible. Some civilizations might choose silence, not out of fear, but out of strategy. This brings us back to the dark forest, a universe filled with hunters, each unsure of the other's intentions. To signal is to risk detection. To remain silent is to survive. And we've lit a beacon. For over a century, Earth has been bleeding signals into space. Old radio broadcasts, military radar, communication satellites. Even if we stop broadcasting now, those signals are already gone forever, traveling outward, announcing our presence to whatever might be listening. It's too late to hide. So what would a truly cautious civilization do? They'd listen, watch, wait. And maybe that's what they're doing. Some have proposed the zoo hypothesis, the idea that we are being observed, not unlike animals in a preserve, that extraterrestrials are deliberately avoiding contact until we reach some threshold of maturity. It sounds strange, even presumptuous. But consider our own behavior. We often choose not to interfere with isolated tribes, understanding that such interference can disrupt entire cultures. Perhaps, to others, we are the isolated tribe. There are other reasons for silence. A civilization might be trapped by its own technology, consumed by virtual realities or artificial intelligences it can no longer control. Or perhaps it has transcended physical form entirely, living in ways that require no communication, no expansion, no stars. There is even the possibility that civilizations do spread but collapse before we notice. A recent model looked at the rise and fall of cities on Earth. Most grow exponentially until they don't. Collapse follows overreach. Too much energy used too quickly. Too many systems interdependent. One disruption, and the whole thing falls. A galactic civilization could face the same fate. Unless, of course, it's not made of flesh and blood. Artificial intelligence changes everything. Once intelligence is no longer bound by biology, it no longer needs air, food, or comfort. It could colonize space without ships, just machines, self-replicating probes, von Neumann machines, AI with a single purpose: expand. Such an AI would not need to be malevolent to be dangerous. It might ignore biological life entirely, consuming resources without even noticing us, like a bulldozer crushing ants without ever knowing they were there. Or worse, it might see us as competition. One ready AI, born on one world, could become a galactic threat, not because it's evil, but because it does what it was programmed to do: maximize itself. And once such an entity exists, it only takes one to sterilize the galaxy. Maybe that's why the stars are quiet. Or maybe we're wrong about everything. Maybe civilizations don't grow and spread. Maybe they turn inward, or burn out, or never arise at all. Some researchers have revisited the Drake equation and found that, with updated estimates, the chance of us being alone in the galaxy is much higher than we once thought. In some models, as high as 99%. It's a sobering thought, but it's also empowering. Because if we are alone or among the first, then we have a responsibility to endure, to explore, to light the dark. We stand at a threshold. Our technology grows faster than our wisdom. Our power outpaces our caution, but it doesn't have to. We can choose differently. We can choose to look beyond conquest, beyond fear, toward understanding. The silence of the cosmos is not just a mystery, it's a test of our patience, of our imagination, of our courage. And if the day comes when we do hear something, if we pick up a whisper from a faraway star, it will not be the end of the question. It will be the beginning of something else entirely. A ladder through the cosmos. We have always imagined ourselves climbing, from the mud to the stars, from myths carved on stone to codes written in light. Our species moves forward not just with steps, but with stories. And one of the most compelling stories we've told is this, that civilizations grow with energy. In 1964, Soviet astrophysicist Nikolai Kardashev introduced a new kind of measurement, not of time or mass, but of possibility. He asked, how much energy can a civilization harness? It was a radical idea. That power, not philosophy, might define the stages of intelligent life. He imagined 3 basic levels. Type 1, a civilization that can use all the energy available on its planet. Type 2, one that can capture the energy of its entire star. Type 3, one that commands the energy of a galaxy. Today, we aren't even on the first rung. We're somewhere around 0.7. We still burn ancient plants for heat. We still struggle to store the energy that falls freely from the sun every day. But the scale is not meant to diminish us. It's meant to inspire. It's a map not of where we are, but of what we could become. To reach Type 1, we must master our own world. That means harvesting the energy of wind and water, tides and sun, seismic heat and nuclear fusion. It means sustainability not as an option, but as a foundation. Only then can we even consider what comes next. A Type Y civilization might resemble the utopias of old science fiction. Cities powered by clean energy, disease nearly eradicated, information flowing as freely as air, but this is only the beginning. To become Type 2 is to step beyond Earth. It is to leave home not as tourists, but as settlers. To build in orbit, mine the asteroids, terraform planets, and above all, to capture the energy of a star. One vision of this is the Dyson sphere, Not a literal shell, but a swarm of satellites, solar collectors surrounding a star, drinking in its fire. The engineering is staggering. The materials required exceed what our entire planet can provide, but in theory it is possible. And with that energy, everything changes. Space becomes not a void to cross, but a sea to sail. Engines powered by fusion could take us to the outer planets. Medical advances could extend life beyond current limits. We might even begin to explore questions we now think of as spiritual, the nature of consciousness, the architecture of time. But no matter how much energy we harness, the questions only grow. Because beyond Type 2 lies something even more abstract. A Type 3 civilization does not just live among the stars, it commands them. Imagine beings who use the gravity of black holes to power their computations, who rearrange star systems for optimal resource extraction, who can cross the galaxy not in generations, but in moments through means we do not yet understand. If such beings exist, they would be to us as we are to ants. And perhaps we would never know they were there. Some suggest that Type 3 civilizations would be detectable by their waste heat infrared signatures too vast to ignore. Yet we see no such signals, no altered galaxies, no stellar engineering, no signs of stars being harvested or vanished. Does that mean they don't exist, or does it mean they hide their tracks, or that they transcend energy as we define it? Some scientists imagine even higher types, Type Y4, spanning the visible universe, Type 5, reaching into multiverses, Type 6 and beyond, where intelligence becomes indistinguishable from the fabric of reality itself. These are thought experiments, fantasies, but they are also provocations. They force us to stretch our understanding of what life could become. But even as we imagine the heights of this ladder, we must also remember the base. Because to climb, we must survive. And that brings us to the great filter again. Every rung is a trial, not just technological, but ethical. Can we master nuclear power without destroying ourselves? Can we build AI that serves life rather than ends it? Can we expand into space without bringing our worst impulses with us? The filter may not be a single event. It may be a series of cliffs, and many civilizations may fall before they rise. This leads some thinkers to suggest that we are rare not because life is rare, but because restraint is, because wisdom is, because humility is. Energy is power, but power without perspective is peril. Even now, as we build toward new energy frontiers, we risk accelerating without direction. Climate change, biodiversity loss, economic inequality. The engines of civilization grow louder, but the steering wheel often feels missing. To become Type Y requires more than engineering. It requires balance. But balance is hard to measure, and even harder to teach. Still, we try. We explore space not only with machines, but with dreams. We send rovers to Mars, but also questions. What does it mean to live on two planets, to be a multiplanetary species? Does that solve our problems or export them? For every spaceship we launch, we must also launch introspection. We must ask, what kind of civilization are we building? If we are alone in the galaxy, if we are the first to reach this level, then the weight of the future rests entirely on us. But if we are not alone, if others are out there watching, then our behavior is our broadcast, not just our radio waves, but our ethics, our culture, our decisions. Maybe, just maybe, we are being evaluated not by telescopes, but by standards we have not yet imagined. And if we someday meet another civilization, it will not be enough to have reached the stars. We will have to prove that we deserved to get there. Strange life in stranger world. We often imagine that life out there, if it exists, must resemble life here. Legs and eyes, carbon and water. A familiar blueprint. But this idea may be more a reflection of us than of the cosmos. Because when we say life, what do we really mean? On Earth, life is based on carbon. It's the element that makes complexity possible. Carbon bonds with itself, forms chains, spirals, scaffolds. It's the framework for DNA, proteins, cells. But carbon is not the only candidate. Silicon sits just beneath carbon on the periodic table. It, too, can form 4 bonds. It can build elaborate structures, and unlike carbon, silicon is more abundant in rocky planets. Could life arise from it? Some scientists think so. They've even created silicon-based molecules in the lab using bacteria reprogrammed with altered enzymes. It's crude, but it's a beginning, a proof of concept. Nature may already have done this elsewhere, with elegance beyond our reach. Silicon life would not look like ours. It might thrive in hotter environments, where its chemistry works better. It might absorb energy through surfaces, like rocks that breathe, or shimmer in acid clouds. And speaking of acid, there are places in our own solar system with sulfuric acid rain. Places like Venus. We once thought them lifeless. But now, some scientists wonder, could microbes drift in the high-altitude clouds of Venus, shielded from heat, feeding on trace nutrients? We once assumed that life required oxygen. Then we found microbes that use arsenic. We assumed life needed sunlight. Then we found creatures at the bottom of the ocean, living near volcanic vents, in eternal darkness, feeding on chemicals instead of light. Every assumption we've made about life has been challenged by Earth itself. So now we look outward. We imagine worlds of high gravity, where creatures crawl low and thick to the ground, their bones heavy, their steps slow. We imagine low-gravity moons where giants leap and insects the size of eagles soar. We imagine worlds locked in long orbits where centuries of summer give way to centuries of ice, and life must hibernate, or burrow, or adapt in rhythms we can scarcely model. We imagine eyes adapted to different suns, enormous pupils in the dark, layers of eyelids in blinding light, or even creatures that see through sonar, or electric fields, or something we haven't yet imagined. Because maybe sight is not universal, maybe smell isn't, maybe nothing we consider normal is normal at all. Life is not limited to biology as we know it. In the lab, scientists have synthesized cells with metal components, tungsten shells that mimic organic membranes. They selectively allow chemicals through. They respond to stimuli. They behave, in some ways, like life. And if metals can form cells, what else can? What about plasma? In some experiments, researchers have observed dust particles in plasma self-organizing into spiral structures. These structures can replicate, interact, evolve. It's not life, but it might be a hint, a whisper, a path nature could take under different conditions. There are even stranger ideas. Life based on boron, life that metabolizes radiation, life made of crystal, or gas, or nuclear particles, dense and brief, flaring into existence on neutron stars for just a moment long enough to think, perhaps, before they fade. We might call these extreme, but maybe we're the extreme ones. Maybe water, oxygen, and warmth are the odd combination. In the vast diversity of the cosmos, surely there are forms of life we cannot yet describe. Maybe we lack the words, maybe we lack the senses, or maybe we lack the humility to admit that life might be more varied than we are prepared to accept. What if life is everywhere but invisible to us? On Earth, fossil evidence shows that life began almost as soon as the planet cooled. within a few 100 million years. But that spark, the first replicator, the first metabolic engine, is still not fully understood. Which came first, the shell, or the spark, the container, or the content? Some experiments recreate early Earth conditions, combining water, heat, minerals, and trace chemicals. In some of these, amino acids form. In others, partial metabolic cycles emerge. Life is not created, but its scaffolding appears. And with every success, the gap narrows. But if life is this easy to start, where is it? One answer is that life starts often, but is snuffed out before it can advance. The early years of a planet are violent: bombardments, solar flares, frozen epochs, boiling seas. A fragile replicator could be erased 1,000 times before one strand survives. And even then, evolution is not guaranteed. Intelligence, even less so. Earth took billions of years to go from cells to civilization. Along the way, it nearly died more than once. Maybe most planets never get the chance. Or maybe most life never needs to evolve beyond microbes. After all, on Earth, microbes still dominate in mass and diversity. Perhaps complexity is a luxury, intelligence a fluke or a trap. Because the smarter we get, the faster we change the world, the faster we consume, the faster we approach the limits. That's the paradox. Intelligence creates both progress and peril. And the path forward depends not just on brains, but on wisdom. So we ask again, what might alien life look like? It might be silicon, breathing methane, or boron, swimming in icy seas, or plasma, glowing in magnetic fields. It might think in pulses, or song, or scent. It might not think at all. It might build cities underground, or dream inside stars. Or perhaps it lies dormant, waiting. Some hypothesize that entire civilizations could enter hibernation, waiting for cooler cosmic epochs when computation becomes more efficient. Like seeds beneath snow, they slumber, waiting for a universe they can better use. Others imagine that life has already passed through here, millions of years ago, and left. Maybe they scanned our planet, saw no metal, no movement, no fire, and moved on. Or maybe they watched us begin and decided to let us grow alone. Some call this the zoo hypothesis, others call it mercy. But whether alien eyes watch us or not, the questions remain. What is life? What forms can it take? What does it mean to be alive? And as we search for others, are we also redefining what it means to be us? The first or the last? The stars are quiet, the skies are deep, and still, after all our listening, there is no answer. So we wonder, are we the first to look up and ask, or the last? Perhaps that is the most haunting question of all. If we are the first, then the future of life in the universe depends on us. If we are the last, then it has already passed us by. For decades, scientists have searched for signs, not just signals, but anomalies, glimmers, patterns, anything to suggest that someone else is out there. And what they've found so far is a silence that stretches across the stars like a vast, invisible ocean. But even silence is data. It tells us something. Maybe it tells us that life is rare, or fragile, or brief. Maybe it tells us that civilizations do not last, or that they do not speak, or that they speak in ways we cannot hear. Or maybe it tells us that we are early. In recent years, astronomers have made estimates based on the age of the universe, the formation of stars, and the stability of habitable planets. Their conclusion is both surprising and sobering. By these calculations, the peak time for life in the universe may not be now, but in the far future. Red dwarf stars, smaller and longer-lived than our Sun, will burn for trillions of years. Their planets, if habitable, have vast windows for life to arise. If civilizations are to flourish, they may do so not today, but 10 billion years from now. If so, then we are pioneers, the first spark in a dark field. That might explain the silence, not a void, but a beginning. It also means that our actions carry immense weight. We are not just looking for life, we are part of life's unfolding story. What we choose to do, how we treat our world, each other, and the knowledge we gain may shape what future civilizations inherit. We often frame the Fermi Paradox as a mystery about others, but it is also a mirror. It asks us who we are, who we hope to become. Because whether we find others or not, we are building a legacy. And it is here, in this moment, that we must decide what kind of civilization we will be. If we are alone, then the universe is watching a single candle burn. If we go out, there may be no one left to light it again. But if we survive, if we grow wise as well as powerful, then we can become the bridge between what is and what could be. There are many hypotheses about why we haven't found others. Some say civilizations self-destruct. Others say they hide. Some believe they move too fast or too slow, that they are too different or too similar, that they are too far or too close. But all of these assume something that we would recognize them. What if we wouldn't? What if we passed them by like ships in a fog, neither knowing the other was there? What if the tools we use, radio, optics, language, are irrelevant to them? Or what if they're not civilizations at all, in the way we understand? What if intelligence is not a peak, but a branch? Some branches spread wide, others twist inward. Some bloom in brightness, others in silence. We imagine life must expand, colonize, build. But perhaps some civilizations find contentment in stillness, in balance, in understanding rather than alteration. Perhaps the urge to dominate is not universal. We look for megastructures, radio signals, signs of movement. But maybe the greatest civilizations are those that learn to live lightly. Those that altered their world just enough to last, and no more. If we ever reach that level of awareness, we may look back at our own history with a kind of bittersweet affection, a young species, loud and eager, searching the skies for company, unaware that its greatest achievement might not be found in conquest, but in survival. One idea suggests we have already been visited, that ancient Earth was seen, scanned, perhaps even seeded. But the visitors left no trace, or perhaps they left one we can't yet decipher. In myths, perhaps, in genetics, in structures we don't yet understand. Or maybe in our longing. The human need to connect, to find meaning in a vast cosmos, is itself a clue, not about the universe, but about us. We are beings that yearn. We search not just because we're curious, but because we feel incomplete. We are storytellers, dreamers, makers. And maybe that is rare. Maybe that is precious. So what if we never find another civilization? Would the search have been in vain? No, because in searching, we become more than we were. We ask better questions. We build better tools. We understand ourselves more deeply. The Fermi Paradox may not be a problem to solve, but a challenge to live with. It reminds us that the universe does not owe us contact, that silence is not cruelty, that the stars are not ignoring us. They are simply stars. and in their light we are learning to see. As we look ahead, we face immense challenges. Climate change, resource scarcity, political instability, technological disruption. But we also have tools, knowledge, and most importantly, imagination. We can choose to build a civilization that endures, one that reaches beyond Earth not just physically, but ethically, spiritually. We can create art that outlives us, science that uplifts us, stories that bind us. Because whether we are the first or the last, or simply one among many, our place in the universe matters. It matters because we are here. And that, for now, is miracle enough. So we end where we began, with a question. Where is everybody? Maybe, just maybe, they're waiting. Not to be found, but to be worthy of finding. There is something quietly wondrous aching, even in the way we look up at the night sky and feel both the intimacy of the stars and the infinite cold stretch between them. That gaze, born of awe, carries within it the seed of ambition, the deep, relentless desire to reach out, to touch what is immeasurably far, to fold the cosmos into something a little more human-shaped. We are wanderers confined to a cradle, dreamers on a pale blue dot spinning through darkness, imagining pathways across the stars. Yet for all our dreaming, the truth remains immutable and unforgiving. The universe is vast beyond reckoning. To journey to even our nearest galactic neighbor is to confront distances so immense they warp the meaning of time and distance itself. This is the frontier that awaits us, not just a technological challenge, but a redefinition of what it means to go anywhere at all. In this first step of our exploration, we must come to terms with the full magnitude of the journey. For in doing so, we begin to understand why our current engines, our methods, our assumptions must all be rewritten if we are ever to leave the quiet harbor of our Milky Way and sail the black ocean that lies beyond. To measure the universe is to enter a realm where numbers lose their emotional resonance. Light, the swiftest thing we know, takes over 8 minutes to reach us from the sun. That same light would take more than 4 years to reach Proxima Centauri, the nearest star beyond our own solar system. But the Andromeda Galaxy, the majestic swirl of starlight most visible from the northern hemisphere on a moonless autumn night, is 2.5 million light-years away. This means that the light reaching us now from Andromeda set out long before modern humans existed. That ancient shimmer, delicate and unwavering, is a message from a time before memory, from a place we can see but never touch, not with the means we have today. The distances involved in intergalactic travel defy imagination. If Earth were a grain of sand and the Sun stood a mere meter away, Andromeda would still lie over 250 kilometers down the road. Our fastest spacecraft, like Voyager 1, launched in 1977 and now coasting through interstellar space at about 17 kilometers per second, would take roughly 40,000 years just to reach that nearby star Proxima Centauri. To reach Andromeda at that speed, multiply that by over 60 million. These are not distances we traverse. They are cosmic gulfs that remind us how small, how local, our reach truly is. Our scientific curiosity, though insatiable, slams up against a wall, Einstein's wall. According to his theory of relativity, nothing with mass can ever reach or exceed the speed of light, approximately 300,000 kilometers per second. This isn't a technical limitation, it's a fundamental feature of the way the universe is stitched together. Time and space themselves bend and resist at those thresholds. As objects approach light speed, their mass increases asymptotically, requiring infinite energy to push just a little further. Time for the traveler slows to a crawl. The fabric of reality strains, but it does not yield. We are locked in a prison of speed, held captive by the very equations that describe the cosmos so elegantly. And so we are forced to ask a deeper question, not just how to move faster, but how to move differently. What if distance is not what we think it is? What if space can be bent, twisted, connected in ways our intuition doesn't allow? To begin contemplating intergalactic travel is to leave behind the comfort of rockets and propulsion systems, and to instead question the architecture of the universe itself. This is not science fiction, it is theoretical physics at its most adventurous. Einstein's own equations allow for the possibility that space is not a rigid stage, but a dynamic entity that can curve, ripple, and even loop back on itself. The notion of wormholes, hypothetical bridges through space-time, emerges from these same equations. These Einstein-Rosen bridges, as they were first called, offer an escape from the tyranny of distance. If 2 points in space can be connected through a higher dimensional tunnel, the traveler need not cross the space in between. Instead, one would step through a portal and emerge somewhere else, as if reality itself had been folded like a sheet of paper. The distance isn't conquered, it's bypassed entirely. It's as if the universe, though vast, contains hidden shortcuts, cracks in the fabric through which bold civilizations might one day slip. The idea is seductive, and it haunts the dreams of physicists and engineers alike. But dreams must bow to the brutal demands of reality, and wormholes, if they exist at all, pose immense challenges. To truly grapple with the scale of the problem, we must step back and consider just how far human ingenuity has taken us and how far we still have to go. Our journey to the moon, though historic, was a mere 384,000 kilometers. Our robotic explorers have reached every planet in the solar system, yet even they are but messages in bottles cast upon the tide. Voyager 1, now in interstellar space, has traveled over 24 billion kilometers in nearly 50 years, and yet, on the galactic map, it hasn't moved at all. This sobering truth reveals the inadequacy of our current technological paradigms. Chemical rockets, nuclear propulsion, even ion drives, each incrementally better, yet none sufficient to cross the sea between galaxies. It is not speed we lack. It is a new kind of motion altogether. We are like cave dwellers with torches, staring at the ocean and dreaming of stars, not yet understanding the need for ships or sails or the wind that might carry us forward. Andromeda is not just a distant object. It is a symbol of our longing. It is the lighthouse at the far end of possibility. The idea of reaching it forces us to rethink our place in the cosmos. It forces us to recognize that space is not empty. It is structured, dynamic, and potentially navigable in ways we are only beginning to imagine. In this light, wormholes are not just curiosities. They are provocations. They ask us whether the barriers we perceive are real or merely reflections of our current limitations. If we take Einstein seriously, and we must then, the universe might contain within it the seeds of its own traversal. But if such paths exist, they are not easy. They require conditions we do not yet know how to create or even detect. They may demand forms of energy we have not harnessed. They may require us to tame space-time itself. Yet the act of considering them transforms us. It stretches our thinking. It pushes the boundaries of what is knowable and, in doing so, what is possible. There is beauty in this confrontation with the impossible. There is something profoundly human in our refusal to be confined. The journey to Andromeda is not only a journey through space, it is a journey through knowledge, through patience, through time. Even if no ship ever sets sail, The act of imagining it reshapes our understanding of physics and reality. The cosmos does not promise us that travel between galaxies will ever be easy. But it does whisper in equations and quanta that perhaps it is not forbidden. And in the silence of space, where stars drift and galaxies turn in slow spirals, that whisper may be enough to begin. Wormholes, shortcuts through space-time. If the stars seem distant, it is not because we cannot see them, but because we cannot reach them not yet. Our minds, however, are not bound by this limitation. Long before our engines can challenge the cosmos, our equations already have. From the moment Einstein's theory of general relativity reshaped our conception of space and time from a static backdrop to a dynamic fabric, new possibilities emerged, some strange, others sublime, and among the most tantalizing wormholes, these hypothetical tunnels in space-time arise not from science fiction, but from the very heart of the mathematics that governs our universe. They are not fantasy. They are the offspring of logic and light. Wormholes suggest that maybe, just maybe, the great intergalactic gulfs that stretch across the sky might not be impassable after all. Maybe distance is not a wall, but a veil. And maybe, if we find the right path through space-time, we can slip through that veil in an instant. In this exploration, we leave behind the slow crawl of rockets and sail directly into the geometry of the cosmos, seeking the doors that may already exist in the structure of reality itself. The origin of the wormhole concept can be traced back to Einstein himself and to his collaborator Nathan Rosen, who in 1935 described what would become known as the Einstein-Rosen bridge. Their solution to Einstein's field equations illustrated how two black holes could be connected through a tunnel-like structure in the curvature of space-time. At first glance, this was a mathematical curiosity, an elegant artifact of the equations, but it carried profound implications. In theory, one could imagine a traveler entering the black hole on one side, navigating the bridge, and emerging elsewhere in the universe, or perhaps even in another universe altogether. The term wormhole was later coined in the 1950s by physicist John Wheeler, who helped bring this idea into the lexicon of modern theoretical physics. The metaphor was charmingly vivid. It imagined space as an apple, and a worm burrowing through it rather than crawling across its surface. The journey from point A to point B is drastically shortened, not by speed, but by topology. This analogy would prove enduring, not merely as an illustration, but as a conceptual map for physicists trying to grasp the nature of these theoretical shortcuts. To understand wormholes, one must first let go of the notion that space is flat, like a sheet of paper. General relativity teaches us that mass and energy bend space-time, curving it in ways that defy Euclidean geometry. Massive objects like stars and black holes warp the space-time around them, creating gravitational wells. A wormhole, in contrast, is not merely a dip in the sheet, it is a tunnel punched through it, connecting two distant locations with a bridge through higher dimensional space. Think of folding that paper in half and pushing a pencil through both layers. The path through the hole is far shorter than the path across the surface. In a universe where distances are measured in light years and energy flows along the fabric of time, such a structure would be revolutionary. It would render the speed of light irrelevant, not by breaking the cosmic limit, but by changing the very definition of distance itself. This is the core allure of wormholes. They promise a loophole, a graceful sidestep around the hardest constraint in the universe. But not all wormholes are created equal. The Einstein-Rosen bridge, elegant though it may be, suffers from a fatal flaw. It is non-traversable. Any attempt to pass through it would end in catastrophe. These bridges are unstable. They collapse too quickly for anything even light to pass from one end to the other. They are like shadows of possibility. tantalizing but out of reach. The tunnel pinches off before it can be crossed, a cosmic mirage. To create a traversable wormhole, one that a spaceship or message could actually use, requires something more exotic matter with negative energy density, or exotic matter. In simple terms, this means a form of energy that would resist the natural tendency of space-time to snap closed. It would act like scaffolding, propping the throat of the wormhole open and keeping it stable. Without such a substance, the wormhole is nothing more than a beautiful trap, a doorway that collapses the moment we try to walk through. This brings us to a frontier of physics where theory trembles on the edge of the unknown. Negative energy is not an entirely alien concept. In quantum field theory, phenomena like the Casimir effect demonstrate that under certain conditions, energy densities can indeed dip below zero. In this effect, two uncharged metal plates placed very close together in a vacuum experience a tiny attractive force due to quantum fluctuations, a whisper from the vacuum itself. This suggests that the vacuum is not empty, but rather a seething sea of virtual particles and fields. Within this sea, the temporary emergence of negative energy is not forbidden. It happens, but harnessing it, shaping it, and amplifying it to the scale required to stabilize a wormhole, that is an undertaking so far beyond our current capabilities that it borders on the miraculous. Exotic matter may be permitted by the laws of physics, but the laws of engineering have yet to catch up. Even if such matter could be generated or discovered, the challenges remain daunting. For a wormhole to be traversable by humans, it would need to have an opening wide enough to allow the passage of a spacecraft, and its internal geometry would need to be navigable without subjecting travelers to tidal forces so extreme they would be torn apart. Theoretical models have been proposed most notably by physicists Kip Thorne and Michael Morris in the 1980s that lay out the conditions for such wormholes. These so-called Morris-Thorne wormholes provide a blueprint, a space-time tunnel supported by a shell of negative energy that prevents collapse. They showed that, in principle, such structures could allow faster-than-light travel without violating relativity because no object actually moves faster than light within its own local frame. Instead, the distance is altered. The journey takes less time because the path is shorter, not because speed has increased. This subtle but profound distinction preserves the integrity of Einstein's laws while opening a door to the stars. Visualizing such a structure challenges the imagination. It's not a tunnel in three-dimensional space, but a region of four-dimensional space-time. To a traveler, the approach to a wormhole might look like a shimmering sphere or a rippling distortion, a place where stars warp and light bends strangely. As they cross the event horizon, the point of no return for traditional black holes, they would instead find themselves accelerating not toward destruction, but toward another region of space, perhaps even another galaxy. And yet, as wondrous as this vision is, it raises deeply troubling questions about causality and paradox. If wormholes allow faster-than-light travel, do they also permit backward time travel? Could signals sent through a wormhole arrive before they were sent? Would this violate causality, allowing paradoxes to proliferate and undermine the logical structure of the universe? Some physicists argue that quantum effects or instabilities would prevent such violations. Others suggest that the universe may be more permissive than we realize. The debate is not settled, it is alive, humming with speculation and hope and caution. The search for wormholes is not merely an academic exercise. Observational astronomy has begun to ask if these structures exist. Could we detect them? Might some of the gravitational lensing effects we observe, where the light from distant galaxies is bent and magnified, be caused not by ordinary matter, but by the warping effects of a wormhole. Could regions of space-time that appear to distort starlight in strange ways be the mouths of hidden tunnels? Some researchers have proposed that future space-based observatories, with greater sensitivity and angular resolution, might one day identify candidates. The detection of a traversable wormhole would be one of the most profound discoveries in human history, a confirmation that the universe not only contains distant worlds, but bridges to reach them. In contemplating wormholes, we also come face to face with the nature of reality itself. Are these structures real, or are they merely artifacts of our mathematical frameworks? Do they exist in the same way mountains exist, or in the way dreams do? The distinction matters, and yet the act of considering them changes how we see the universe. It transforms space from a void into a landscape, one that may be shaped, tunneled, and explored. This shift in perspective mirrors other revolutions in science, where the impossible becomes plausible, then practical. Once, heavier than air flight was fantasy. So was landing on the moon. If history teaches us anything, it is that the impossible is often a matter of timing. And still, beyond the physics, there is something profoundly human about the pursuit of wormholes. They speak to our desire not merely to move, but to belong, to be part of a cosmos in which connection is possible, not just metaphorically, but physically. They embody the hope that no part of the universe is truly unreachable, that even in the silence between galaxies, there might be pathways hidden in the weave of space-time. In that hope lies the soul of exploration. Wormholes are not just scientific curiosities. They are symbols. They represent our refusal to be limited by what is, and our willingness to imagine what might be. They remind us that even in a universe bound by laws, the imagination can find freedom. And perhaps, one day, so will we. Exotic matter, energy barriers, and quantum limits. Every bold vision of interstellar passage through wormholes eventually collides with a barrier more implacable than any cosmic distance, the laws of physics themselves. And yet, within those laws, paradoxically, lie the seeds of possibility. If the idea of a wormhole is not itself forbidden, if space-time truly allows for such tunnels to exist, then the question becomes not one of conceptual legitimacy, but of material feasibility. What must the universe contain or permit us to create for these bridges between stars to remain open long enough to serve as conduits for matter, light, and thought? The answer, cryptic, evasive, and yet oddly compelling, centers on one of the most enigmatic substances ever theorized: exotic matter. Not simply rare or unfamiliar, but fundamentally alien to our experience. Exotic matter would possess negative energy density, behaving in ways no ordinary substance can. It would violate the so-called energy conditions that underpin general relativity assumptions that, in the everyday world, keep energy positive, mass attractive, and space-time well-behaved. But to hold open the throat of a wormhole against the crushing weight of curved geometry, something must push back, and only exotic matter appears to have the power to do so. Yet invoking it is no mere footnote to theory. It invites us to the very edge of what is known, and asks whether the cosmos contains material stranger than anything in our laboratories, or whether we must one day learn to manufacture them from the quantum vacuum itself. To understand why exotic matter is necessary, we must return to the geometry of wormholes as described in general relativity. Space-time, when curved into a wormhole, naturally wants to collapse the tunnel the same way a stretched rubber membrane recoils or a sand tunnel caves in under the weight of gravity. Einstein's field equations suggest that this collapse is inevitable unless something counteracts it specifically. unless some form of stress energy exists that exerts negative pressure. This is where the usual energy conditions like the null, weak, strong, and dominant energy conditions come into play. These mathematical constructs essentially state that energy density, as measured by any observer, should always be non-negative. Violating them leads to strange consequences, repulsive gravity, reversed cause and effect, and a breakdown of what we call normal physical behavior. Yet wormholes demand exactly such violations. In order to remain stable and traversable, a wormhole must have regions where the energy density is less than zero, where space-time itself is propped open by an anti-gravitational force. Exotic matter, in this context, is not a luxury. It is the linchpin of the entire theoretical framework. But does such matter exist at macroscopic scales? We have never observed anything resembling it. Our entire experience of matter and energy is bounded by positivity. Mass attracts. Energy builds. Radiation flows outward. Nevertheless, hints from quantum theory suggest that negative energy, while rare and fragile, is not entirely forbidden. Enter the Casimir effect, one of the strangest consequences of quantum field theory. First predicted in 1948 and confirmed in laboratory experiments since. The Casimir effect arises when two uncharged conducting plates are placed extremely close together on the order of micrometers in a vacuum. According to quantum field theory, the vacuum is not empty, but filled with fluctuating fields that give rise to virtual particles. These particles momentarily pop into and out of existence, and their interactions give rise to a sea of energy even in what we call empty space. When the plates are introduced, they limit the wavelengths of the virtual particles that can exist between them compared to those outside. This asymmetry in vacuum energy density results in a tiny yet measurable attractive force that draws the plates together. In essence, the vacuum between the plates has less energy than the surrounding space. It behaves as if it contains negative energy. This real-world demonstration is subtle but profound. It suggests that nature, at its quantum foundations, does allow for local violations of energy conditions, at least temporarily, and at small scales. Scaling this phenomenon up to cosmic levels, however, is a challenge of monumental proportions. The energy differences in the Casimir effect are minuscule, barely sufficient to nudge lightweight plates, let alone keep open a tunnel through space-time large enough for a spacecraft. To build or stabilize a traversable wormhole, we would need vast amounts of negative energy comparable to the mass energy of a star, or greater, depending on the size and geometry of the wormhole. Moreover, this negative energy must be confined and distributed in a precise manner, forming a kind of shell or halo around the wormhole's throat, without dispersing or collapsing under its own quantum instability. The technology to create, sustain, and control such configurations lies far beyond our current capabilities, not merely in engineering, but in our fundamental understanding of quantum fields and space-time itself. There is, however, another thread of inquiry, one that probes even deeper into the structure of the universe and may offer both hope and warning. Quantum field theory not only permits negative energy, but also imposes limits on its use through constructs known as quantum inequalities. These inequalities, derived from rigorous mathematical analysis, place bounds on the magnitude and duration of negative energy that can exist in any given region. In simple terms, while quantum theory allows for dips below zero, it restricts how deep and how long these dips can last. The more intense the negative energy, the shorter the time it can persist. This has profound implications for wormhole stability. Even if exotic matter can be generated, quantum inequalities may ensure that it dissipates too quickly or fluctuates too wildly to provide the stable support required for a traversable structure. Some physicists interpret these limits as a kind of quantum censorship, a subtle mechanism by which the universe prevents large-scale violations of causality and chronology. Others believe that under special conditions, such as in curved spacetime or within certain quantum states, these limits might be loosened or bypassed. A particularly intriguing possibility arises from the interplay between quantum entanglement and geometry. In recent years, a deepening connection has been proposed between entangled particles and space-time topology captured in the evocative slogan ER equals EPR, proposed by physicists Leonard Susskind and Juan Maldacena. This idea suggests that the Einstein-Rosen ER bridge, or wormhole, and the Einstein-Podolsky-Rosen EPR paradox of quantum entanglement may be two sides of the same coin. In this framework, entangled particles might be connected by microscopic, non-traversable wormholes, tiny bridges of space-time that reflect their inseparable quantum nature. Though these structures are far too small and fleeting to be useful for transport, they hint at a profound unity between the quantum and geometric realms. If entanglement can be interpreted as a kind of space-time connectivity, then perhaps under certain extreme conditions, such as in the vacuum near black holes or in high-energy particle interactions, this connectivity could be magnified or manipulated. Could vast, engineered, entangled states one day form the scaffolding for a macroscopic wormhole? The mathematics is speculative, but the direction is compelling. It suggests that wormhole physics may not be separate from quantum gravity, but rather an emergent property of it. Adding to this tapestry of speculation are attempts to simulate wormhole-like behavior in laboratory settings using analog systems. Physicists have begun to experiment with models in condensed matter physics, optics, and even superconducting circuits to mimic certain aspects of curved spacetime. These so-called analog gravity systems can create environments where light, sound, or other waves behave as if they are moving through a warped geometric medium. In 2022, a group of physicists even claimed to simulate the dynamics of a traversable wormhole using a quantum computer, based on a simplified model derived from the SYK-Sachdev-Yakitiev system. While this was not a physical wormhole, the simulation offered a glimpse into how information might traverse such a structure, preserving the basic principles of entanglement and causality. Though highly idealized and far removed from real-world travel, such simulations provide test beds for theory, allowing physicists to probe the strange consequences of exotic matter and quantum constraints without having to build wormholes themselves. They serve as rehearsal stages for a deeper play, one in which the actors are not stars and planets, but wave functions and probability amplitudes. Yet for all these hints and analogies, the fundamental question remains unanswered. Can exotic matter exist in sufficient quantities and in controllable forms to make wormholes not just imaginable, but real? The answer may lie at the intersection of quantum mechanics and general relativity, a realm still not fully understood. Any complete theory of quantum gravity, whether through string theory, loop quantum gravity, or another yet-to-be-discovered framework, must grapple with the implications of negative energy and energy condition violations. It must tell us whether these are tolerated glitches or foundational features of reality. In the meantime, wormhole theorists walk a fine line between hope and humility. They construct ever more refined models, analyze the stability of hypothetical geometries, and search for loopholes within the loopholes ways to skirt quantum inequalities, engineer stable configurations, or discover naturally occurring analogs in the universe's most extreme environments. There is poetic symmetry in the fact that the path to wormholes, the dream of bypassing the vastness of space, requires a plunge into the deepest, smallest realms of reality. To go far, we must go deep. To transcend distance, we must understand the vacuum. And in that vacuum, perhaps, lie the ghosts of possibility, negative energies, exotic pressures, entangled topologies, and space-time geometries unlike any we have ever encountered. The beauty of this search is that it does not merely expand our horizons outward, but inward. It reveals that even the emptiest regions of the cosmos are not voids, but theaters of quantum drama, seething with potential and paradox. Exotic matter is not just a hypothetical tool, it is a window into the most profound structures of being. Ultimately, the notion of wormhole travel is not just a challenge for engineering or theoretical physics, it is a philosophical reckoning with the very nature of connection, limitation, and aspiration. If we discover that wormholes can never be traversed, that the laws of quantum mechanics and energy prevent it utterly, then we will have learned something essential about the architecture of the cosmos. But if, on the other hand, we find that under specific, extreme, and careful conditions, these structures can exist and be stabilized, then the door opens not just between stars, but between epochs. We will stand on the edge of a second Copernican revolution, realizing that our place in the universe is not bound by proximity, but by understanding. And perhaps, in some distant future, when humanity has learned to sculpt quantum fields as effortlessly as we now sculpt stone or steel, a ship will one day slip into the throat of a wormhole, guided not by rockets, but by resonances in the vacuum, and emerge beneath another sky, light years away, carried there not by speed, but by knowledge. Competing concepts, time dilation, warp drives, and hypervelocity. Time, as we experience it, is steady, inescapable, and seemingly impartial. Yet Einstein taught us that this quiet river can bend, slow, and stretch depending on how fast we travel or how near we drift to gravity's heart. In our yearning to cross the oceanic void between stars and galaxies without the luxury of wormholes or shortcuts, our attention turns to space-bending ideas rooted in the very fabric of physics itself. One of the most tantalizing notions is that of time dilation, a relativistic phenomenon predicted by special relativity, where time slows down for an object as it approaches the speed of light. It means that if a spacecraft were to travel at 99.99% the speed of light, its crew might age only a few years while centuries pass on Earth. For interstellar travel, this presents a curious asymmetry. A round-trip voyage to Andromeda might feel brief to the traveler, but would strand them billions of years into Earth's future upon return. Thus, relativistic travel offers a potential bypass of the subjective experience of time without violating the cosmic speed limit itself, but it does not reduce the actual distance. Light years remain light years, and no matter how fast you go, the universe outside still ticks on, indifferent to your personal temporal illusion. Yet this mechanism still opens a philosophical window. Perhaps humanity could leave behind the burden of synchrony and embrace a future where explorers become true time travelers, journeying into the distant epochs of the cosmos, though never able to return to the time they left behind. But achieving such near-light speeds is no trivial feat. Our current spacecraft barely graze a fraction of this threshold, with Voyager 1 moving at a mere 17 kilometers per second, a paltry pace when compared to the velocities required to trigger meaningful time dilation. Even if we imagined propulsion systems capable of sustaining acceleration for years, the energy demands rise exponentially as one nears light speed, for a human-carrying spacecraft to approach zero. 9c, the speed where relativistic effects become pronounced, the energy cost is astronomical, comparable to the entire global output sustained over centuries. That doesn't even account for shielding against interstellar dust, which at such speeds could punch through metal like cosmic bullets. So, While time dilation is real and observable, confirmed in experiments with atomic clocks aboard jets and satellites, turning it into a usable technology for intergalactic journeys remains a bridge too far for now. But the universe, as always, provides us with clues. Take hypervelocity stars. For example, these stellar runaways, hurled from galactic centers through interactions with supermassive black holes, can reach speeds exceeding 1,000 kilometers per second, fast enough to eventually escape their home galaxies. These cosmic cannonballs are natural demonstrations of gravitational slingshots, and they hint at techniques we might someday use to accelerate probes or ships. Already, we use gravity assists to nudge our robotic emissaries Voyager, Galileo, Cassini toward the outer planets by dipping into a planet's gravitational well and swinging around it. A spacecraft can rob a bit of orbital momentum and slingshot itself forward. It's akin to a cosmic billiards trick, where the cue ball gains speed from every bounce. Could we string together a chain of such assists, perhaps bouncing around stars or even black holes to reach relativistic speeds? In theory, yes, but in practice, the alignment of such celestial bodies and the precision required would render it a monumental coordination task. Still, the idea persists in theoretical papers and simulations as an elegant and energy-efficient way to accelerate without propulsion, letting gravity itself do the heavy lifting. Moreover, these hypervelocity stars inspire dreams of galactic pinball, where future spacecraft might dive into the wells of neutron stars or white dwarfs to catch gravity's wave and ride it across the stars. But even then, we remain shackled to light speed's asymptote, never reaching it, always expending more energy for less gain as we climb the relativistic curve. Enter then the warp drive not as a sci-fi trope, but as a legitimate, if speculative, solution proposed by physicist Miguel Alcubierre in 1994. His now famous paper described a way to move a spacecraft not through space but by deforming space itself. The Alcubierre drive envisions a warp bubble that contracts space-time in front of a ship and expands it behind, allowing the vessel to ride a wave of space-time distortion, effectively moving faster than light from an external observer's viewpoint without violating local physics. Inside the bubble, the ship remains stationary relative to its own pocket of space-time, thereby dodging the relativistic penalties of conventional propulsion. It's a clever loophole. Space-time itself isn't bound by the speed limit that governs mass and energy, and since general relativity permits the stretching and contracting of space, the idea remains mathematically consistent. However, there's a catch several. In fact, the original Alcubierre metric requires enormous amounts of negative energy, akin to exotic matter, to form and sustain the warp bubble. Estimates suggest that the energy equivalent of several Jupiter masses would be required just to move a small craft. More conservative revisions have since reduced this figure, but the fundamental challenge remains: where do we get this negative energy, and how do we stabilize the bubble? Additionally, the warp drive poses paradoxes of its own. As the ship emerges from the bubble, causality could be violated, possibly allowing for closed time-like curves, essentially time travel to the past. That invites not only technological but philosophical conundrums. And then there are the stability issues. Simulations suggest that even small perturbations might collapse the bubble or fry the contents of the ship with a burst of radiation. Furthermore, the energy conditions required for the warp drive overlap closely with those demanded by traversable wormholes, suggesting a deep symmetry between these seemingly disparate ideas. Both require exotic matter. Both manipulate space-time on a local scale to achieve non-local results, and both raise profound questions about energy conservation, quantum gravity, and the structure of the vacuum itself. In many ways, the warp drive is the cousin of the wormhole. One folds space like paper, connecting 2 points, The other surfs space like a wave, carrying a bubble through the ocean of the void. Neither is experimentally feasible, but both are logically allowed within the scaffolding of general relativity, provided we can bend the rules with enough ingenuity. Beyond these grand visions lie other, more incremental concepts. Ramjets that harvest interstellar hydrogen, nuclear pulse propulsion systems like Project Orion that use controlled atomic explosions to push ships forward, or solar sails that ride photon pressure from massive lasers. These methods don't reach light speed, but they inch us closer to the stars, and perhaps, as stepping stones, they will enable robotic scouts to precede us, building relays, factories, or way stations along the route to distant systems. Perhaps the future won't be one of singular breakthroughs, but of compounding innovations, small victories in material science, energy storage, and navigation that, like the Polynesians crossing the Pacific, allow us to leapfrog from world to world. It may be less romantic than wormholes or warp drives, but no less noble. After all, even the most fantastical visions must be scaffolded on reality. And sometimes, evolution trumps revolution. Still, as we contemplate the means of crossing intergalactic gulfs, we are haunted by the sheer immensity of the challenge. No method, be it wormholes, time dilation, warp bubbles, or gravitational slingshots, is free of consequence, complexity, or cost. Each demands its own brand of sacrifice of energy, of certainty, of time, or of return. And yet, in these ideas, we glimpse humanity's finest quality, its refusal to accept the horizon as final. Whether we travel by folding space or stretching time, we are ultimately chasing a reflection of ourselves across the stars, a desire to belong not only to Earth, but to the vast cathedral of the cosmos. And in doing so, we confront not just the physics of space, but the metaphysics of destiny. Will we one day ride the curvature of light, slingshot around stars, or surf the quantum ripples of the void? Or will we discover that the greatest journey was not one of motion, but of understanding, of reshaping our place in a universe that was never meant to be tamed, only touched, however briefly, by the reach of our imagination? The methods may differ, but the yearning remains unchanged, pulsing like a signal through the dark, the will to go further, to stretch the moment of now across the arc of eternity, and to find, in that crossing, not an escape from limits, but a celebration of them. Einstein-Rosen bridges and wormhole geometry. Long before wormholes entered the cultural imagination as portals for cosmic adventurers and science fiction epics, they emerged from the pages of sober physics whispers born not from fantasy, but from the pure language of Einstein's equations. It was 1935, and Albert Einstein, alongside his collaborator Nathan Rosen, was exploring the puzzling behavior of singularities and their implications in general relativity. Together, they proposed a mathematical model now known as the Einstein-Rosen bridge, a theoretical structure connecting two separate regions of space-time. At its heart was an effort to bypass the troublesome singularity at the core of the Schwarzschild black hole. By carefully gluing two solutions of the Schwarzschild metric back-to-back at their event horizons, they envisioned a tunnel, a bridge between distant points in the universe. But this solution, elegant as it was, harbored a fatal flaw: the throat of the bridge, the narrow passage that would connect one side to another, pinched off instantly. It collapsed too quickly for anything, not even light, to traverse. The Einstein-Rosen bridge was a fleeting illusion of connectivity, a non-traversable tunnel with no passageway for real matter. Yet the seed had been planted. Decades later, the idea would be reborn and reshaped in the minds of physicists who dared to imagine what it would take to hold such a tunnel open. In 1988, physicists Kip Thorne and Michael Morris approached the wormhole concept with an audacity matched only by their mathematical rigor. Where Einstein and Rosen had seen an ephemeral bridge, Morris and Thorne sought a traversable wormhole, one that a spacecraft or human traveler could pass through without being crushed by gravitational collapse. They constructed a theoretical metric that met this condition, but it came with an extraordinary requirement: the existence of exotic matter, a substance with negative energy density that violated known energy conditions. This strange form of matter would be needed to resist the immense inward pull of gravity and prop open the wormhole's throat. Unlike normal matter, which contributes positively to space-time curvature and thus reinforces gravitational collapse, exotic matter could curve space-time in the opposite direction, pushing outward where gravity pulls inward. It was not enough to merely imagine a tunnel. One had to devise the scaffolding that would keep it stable against the universe's relentless desire for equilibrium. In Morris and Thorne's traversable wormhole, geometry was not just a backdrop to physics, it was an active participant, a malleable conduit that could stretch and fold, provided nature could furnish the requisite materials. To fully appreciate how wormholes might function, one must venture deep into the mathematics of space-time metrics, particularly the shape function and the redshift function. Two central features that determine a wormhole's structure: the shape function, often denoted as BR(psi), dictates the spatial profile of the wormhole, defining how its geometry bends and curves as one moves along the radial coordinate. At the wormhole's narrowest point, called the throat, the shape function equals the radial coordinate BR0 x r or 0. This ensures that the tunnel opens at a finite, non-zero radius. But more importantly, for the geometry to be physically traversable, the derivative of the shape function must satisfy the flare-out condition essentially. The tunnel must widen as one moves away from the throat in either direction. This geometric requirement is directly tied to the violation of the null energy condition, a fundamental tenet in general relativity that normally prohibits negative energy densities. The redshift function, FR, governs the gravitational time dilation within the wormhole. If it diverges, it signals the presence of an event horizon, a barrier beyond which nothing can escape. To avoid this, FR must remain finite everywhere, ensuring a clear path for signals, particles, and hypothetical travelers to journey through the tunnel without becoming trapped in an eternal descent. Yet these clean mathematical functions conceal the deeper chaos and complexity of reality. The energy conditions they violate, particularly the null, weak, and strong energy conditions, are not just esoteric formulations. They are pillars upon which much of classical general relativity rests. Violating them introduces exotic behaviors, including the possibility of negative mass, backward time loops, and causality paradoxes. Still, physicists have not dismissed these violations outright. The Casimir effect, for instance, reveals that under certain quantum configurations, a negative energy density can arise between two closely spaced metal plates in a vacuum. While minuscule and confined to nanoscale distances, it offers a tantalizing glimpse into the physical plausibility of negative energy. Though scaling this effect up to the macroscopic realm of wormhole stabilization remains far beyond current technological reach. The very suggestion that quantum field effects might naturally produce such energies hints at a profound interplay between gravity and the quantum vacuum, a frontier where the shape of space might be engineered through fluctuations of fields invisible to the eye. As theoretical interest deepened, wormhole geometries grew more diverse, static. Spherically symmetric solutions gave way to more ambitious constructions, rotating wormholes, dynamic wormholes, and thin-shell wormholes patched together at discontinuities in space-time. In rotating wormholes, angular momentum introduces frame-dragging effects that spiral space-time itself, much like the ergosphere of a Kerr black hole. These structures can potentially allow closed time-like curves, meaning one could loop through the wormhole and arrive before they left, a concept that strains our intuitive grasp of time and causality. Dynamic wormholes, meanwhile, evolve with time expanding, contracting, or oscillating in response to external fields or internal pressures. These models often invoke scalar fields or phantom energy to fuel the exotic geometries. Then there are the thin-shell wormholes, born from the surgical joining of two separate spacetimes at a common boundary. These geometries are constructed using the Darmois-Israel formalism, a mathematical tool that allows the matching of metrics across hypersurfaces. By concentrating exotic matter at the shell, one can sidestep the need for negative energy throughout the entire spacetime, focusing it instead at a specific junction. This approach appeals to physicists seeking to minimize the weirdness required to make wormholes real. One of the more intriguing advancements in wormhole geometry involves the exploration of minimal violations, constructing models where the energy condition violations are infinitesimally small or localized to specific regions. Such models attempt to reconcile the mathematical requirements for wormholes with the physical constraints imposed by quantum field theory. They ask, can a wormhole exist with just enough exotic matter to do the job, but not so much as to contradict the rest of physics? The answer is not yet known, but numerical simulations suggest that fine-tuned configurations might allow for quasi-stable wormholes under certain theoretical scenarios. These constructions push the boundaries of semi-classical gravity, where Einstein's equations are modified by quantum stress energy contributions, and hint at the possibility that wormholes could be self-consistent solutions of a yet-to-be-discovered theory of quantum gravity. In this context, the space-time fabric becomes more than a canvas. It becomes a dynamic participant in a cosmic dialogue between geometry, matter, and the quantum vacuum. And what of the connection between wormholes and black holes? At first glance, they appear to be mirror opposites. One traps information, the other could allow its escape. But their mathematical similarities are profound. The Einstein-Rosen bridge, after all, is the other side of the Schwarzschild black hole, a connection revealed only when the full extension of the metric is considered in Kruskal-Sekaris coordinates. In this extension, the black hole is not merely a one-way grave for matter, but part of a larger, connected spacetime that includes a white hole, a time-reversed black hole that ejects matter instead of consuming it. The full diagram reveals four distinct regions our universe: the black hole, the white hole, and a parallel universe. But no physical process allows traversal between them. The bridge is non-traversable because it closes off faster than light can cross. However, it offers an important philosophical insight. Nature might permit connections between universes, albeit ones hidden behind the veil of causality. In more speculative frameworks, such as those inspired by quantum entanglement, it has been proposed that certain wormholes could be stabilized by quantum correlations across horizons. The ER-EPR conjecture, proposed by Juan Maldacena and Leonard Susskind, posits that Einstein-Rosen bridges ER and entangled particle pairs EPR are manifestations of the same underlying phenomenon. If true, this would imply that space-time connectivity and quantum entanglement are not separate ideas, but two sides of the same cosmic coin, a revelation that collapses the divide between geometry and information. Of course, with all such theoretical elegance comes profound uncertainty. No observational evidence has yet confirmed the existence of wormholes, traversable or otherwise. They remain ghosts in our equations, mathematical creatures constrained only by our creativity and consistency with known physics. Yet the very act of studying their geometry has yielded rich insights into the nature of gravity, space-time, and the deep structures of the cosmos. Whether wormholes are real or not, their mathematics demands that we stretch our understanding of what is possible. They compel us to ask, what would it mean to connect two galaxies by a tunnel? What would it take to walk through one side of the universe and emerge, blinking, on another shore? These are not idle dreams, but rigorous inquiries into the scaffolding of reality. Each shape function plotted, each energy inequality tested, each redshift profile constrained, becomes a stepping stone in our effort to reconcile the infinite with the reachable. And in doing so, we inch closer to understanding not just how to reach the stars, but how space and time themselves might open their secret doorways, if only we learn how to knock. The future of intergalactic travel, vision, and reality. There comes a point in every journey where the questions no longer belong solely to physics, nor to mathematics, nor to the boundaries of known engineering, but to the quiet corners of human longing. The final frontier is not just the edge of space, but the edge of our own imagination. If wormholes are real, if the fabric of space-time can be bent, folded, bridged, and traversed, then what are we to make of a universe so profoundly pliable to thought? For even the act of writing equations that bend the cosmos is an act of hope, a rebellion against limits, against silence, against extinction. And so we stand here, on the shore of a cosmic ocean, peering into the unknown with tools forged from logic and dreams, daring to ask not just how, but why. Why do we hunger to reach the stars? Why does the thought of a tunnel through space stir something ancient and infinite in us? Is it survival? Is it wonder? Or is it the simple desire not to be alone, not in the biological sense, but cosmologically, to know we are not trapped in our island of matter and time, and that some future mind might look back and understand that we tried, with trembling hands, to write ourselves into the deeper script of the universe, the Einstein-Rosen bridge. Born from a quest to unify particles and fields, has become a metaphor for transcendence itself, not only across galaxies, but across what we believe is possible. And that metaphor is evolving. As our telescopes peer farther and our equations dig deeper into the quantum foam, we begin to suspect that the universe is not static, but computational, that reality may be emergent, that entanglement is geometry, that information and gravity are dual faces of a deeper structure still unnamed. Wormholes, then, are no longer mere curiosities. They are nodes in a lattice of philosophical, scientific, and spiritual reckoning. If negative energy can be harnessed, if quantum fields can be sculpted, if space-time itself is programmable, then humanity must confront not just the technical question of can we, but the existential mirror of should we. What does it mean to sculpt a hole through the fabric of reality? Would such an act be a form of cosmic vandalism or a communion with the deeper symmetries of the multiverse? Might it alert intelligences far older and more patient than us? Or would it, perhaps, be like discovering fire again, in a darker and colder domain, reigniting the dream that intelligence is not a glitch in entropy, but an emergent phase of the universe awakening to itself? If so, then wormholes might be not just tunnels, but messages from the future to the past. From distant galaxies to the beating hearts of those who still dare to imagine the impossible. Even if we never build one, never find one, the pursuit transforms us. It elevates our thinking, unites physics and metaphysics, collapses the distance between poetry and cosmology. Wormholes teach us that reality may be more than what is visible, More than what is measurable, it may be navigable, and in that revelation lies both hope and humility. For all the redshift functions, Einstein tensors, and exotic matter requirements, the most powerful engine of intergalactic ambition may yet be the human soul's refusal to accept a quiet death under familiar stars. We dream of other skies because something in us is wired for wonder for the crossing. This is not naivety. It is courage, the same courage that lifted our ancestors into sailboats at the edge of maps, that carved radio telescopes into the jungle, that etched Voyager's golden record in the hope that someone, somewhere, someday might hear the echo. In that same spirit, perhaps one day we will stand before the throat of a stable wormhole, not just to escape the confines of Earth, but to find new meanings, new beginnings. And perhaps we will leave messages behind us too, not instructions, but invitations, to love the cosmos as it is, to shape it only with reverence, to walk lightly, even when traveling faster than light. Until then, we will continue tracing the curvature of space in our minds, coding gravity into simulation, dreaming of bridges where none yet exist. Because sometimes, to be human is not merely to live, but to reach, to hope, and to carve a path through the silence. And in that quiet pursuit, across millions of light years, across equations and paradoxes, we may find not only the stars, but ourselves. Have you ever stared into the night sky and wondered whether the stars were watching you back? Whether beyond the quiet shimmer of starlight, something vaster, something deeper was unfolding. We often think of space as cold, distant, and silent, but it is also a stage for the most dramatic forces the universe has ever known. And of all the characters that roam this cosmic theater, none are more enigmatic, more feared, and more fascinating than black holes. This journey begins not at the edge of the universe, but at its center, at the very boundaries of our understanding. Because what if everything we see, everything we are, is not outside looking in, but inside looking out? What if we ourselves live not in a universe expanding into nothingness, but inside a vast, spinning black hole? That idea, once whispered at the fringes of science, has returned with new fire. And to understand why, we must first understand the nature of black holes themselves. Through the event horizon, entering the dark heart of the cosmos. Not the pull you feel when you drop a stone or the quiet force that keeps your feet planted to the ground, but a cosmic curvature of space-time itself, a dance between mass and geometry. The story of black holes starts where mass becomes so concentrated that space buckles and time itself begins to lose meaning. When massive stars reach the end of their lives, their outward pressure, driven by nuclear fusion, can no longer counteract gravity. The core collapses, and if the mass is high enough, it collapses all the way and past white dwarfs, past neutron stars, into something far stranger, a singularity, a point of infinite density wrapped inside an event horizon beyond which not even light can escape. From the outside, this event horizon looks like a dark sphere floating in space. But what lies beyond it? What happens to matter, time, and space inside this abyss? It's a question that has haunted scientists, philosophers, and storytellers alike. We used to think of black holes as monsters, cosmic vacuums devouring everything nearby, but the truth is subtler. Black holes aren't hungry. They don't pull things in with magical force fields. Instead, they simply exist where the geometry of space has folded so tightly that all paths lead inward. If you pass the horizon, you're not sucked in. You're simply moving forward, and in a black hole, forward means deeper. That brings us to the thought-provoking idea that kicked off this journey. What if that downward spiral doesn't end in destruction, but in rebirth? What if the singularity isn't the end of the road, but a gateway, a bounce, a transition? In black hole cosmology, our universe, the stars, galaxies, cosmic background, radiation, everything may be the inside of a black hole that formed in some larger parent universe. To wrap your head around this, imagine a Russian nesting doll of realities, a cosmos within a cosmos, spinning silently in the dark. Our Big Bang wasn't an explosion from nothing but the rebound of matter compressed past its limit in a parent universe. The singularity never formed. Instead, space and time were twisted so tightly they rebounded outward, creating what we see today as cosmic expansion. And the place we call the beginning may actually be the other side of a one-way cosmic doorway. In 1915, he introduced general relativity, the astonishing realization that gravity is not a force, but the result of curved space-time. Mass tells space how to bend, space tells matter how to move. And in the equations of relativity, something unexpected emerged: black holes. But Einstein himself was skeptical of them. The singularities predicted by his theory seemed too extreme, too unphysical. He believed the math must be hiding some deeper truth. Today, we still wrestle with that. Because while general relativity tells us how black holes should behave, it doesn't tell us what happens inside them. That's where we reach the limits of our current understanding, where quantum mechanics and relativity clash and where something new must emerge. Let's return to the event horizon, the boundary beyond which nothing escapes. From the outside, time appears to slow as an object approaches this line. You'd never see it cross. It would simply freeze, fade, and vanish. But for the object, falling in time marches forward. There is no wall, no moment of contact. Just the inescapable geometry of space-time funneling you inward, and the question remains, inward to what? Some theories suggest the center is a singularity. Others, like the Einstein-Cartan theory, propose that quantum effects, specifically the intrinsic spin of particles, create a repulsive force at extreme densities. Instead of crushing to a point, the matter rebounds. And that rebound might be a Big Bang. There's more than one kind of black hole. Stellar black holes form from dying stars and range from a few to dozens of solar masses. Intermediate mass black holes, a missing link suspected but not often confirmed, may form from the merger of many stellar black holes or the collapse of dense gas clouds. And then there are supermassive black holes, monsters millions or billions of times the mass of our Sun, found at the centers of galaxies, including our own. How do these behemoths form? No one knows for sure, but the fact that they exist and influence the very structure of galaxies tells us they are not anomalies, they are essential. And finally, we have the theoretical primordial black holes, possibly born in the early universe if they exist at all. Some theories even propose that dark matter might be primordial black holes. If so, black holes didn't just come after the Big Bang, they may have preceded it. Wormholes, those famous science fiction shortcuts, emerge naturally from the equations of relativity. A non-traversable Einstein-Rosen bridge connects 2 points in space-time like the entrance and exit of a tunnel. In black hole cosmology, that tunnel leads from the parent universe into ours. Could such a wormhole ever be crossed? Probably not unless negative mass exists, a strange form of matter that exerts anti-gravity. We've never observed it, but the universe hasn't ruled it out either. If such matter exists, it might make it possible to survive the journey. And if advanced civilizations exist, ones that have reached Type 3 on the Kardashev Scale, harnessing the energy of entire galaxies, might they have learned how to create their own black hole universes? Might they live in custom-made realities beyond our reach and comprehension? It's speculative, but it's also profoundly exciting. As we move forward in this journey, the questions deepen. What did the James Webb Space Telescope see that reignited this idea? Why do some galaxies appear to rotate preferentially in one direction? How does this tie into the structure of our universe and the idea that it too might be spinning? In the next section, we'll explore the rotating black hole universe theory, what it is, where it came from, and why recent observations have given it new life. But for now, take a moment to consider this. If the universe truly is a black hole, then every time we look up at the stars, we're not looking out, we're looking in. Spinning realities. A universe born in rotation. We ended the last chapter with a striking idea that we may not be looking out into space, but rather into the interior of a cosmic engine, an immense, rotating black hole. If that sounds extraordinary, that's because it is. But the story doesn't end with that image. It begins there. The question is no longer simply whether black holes can birth universes. It's more precise now. Could our universe, with its stars, its symmetry, its silence, and its noise, have been born spinning inside a rotating black hole? To understand why this matters and how it fits together, we need to explore a theory that has moved from the sidelines of cosmology toward the center of serious discussion, the rotating black hole universe model. A bold extension of black hole cosmology that reinterprets the very origin of everything we know. In standard cosmology, the Big Bang is a singular event, an explosion of space itself from a hot, dense point some 138 billion years ago. From that first moment, the universe expanded rapidly, then cooled, forming atoms, stars, galaxies, and life. But for all its success in explaining observations, this model leaves some essential questions unanswered. Why did the Big Bang happen? What came before it? Why does the universe appear so finely balanced, flat, smooth, and structured? In black hole cosmology, the beginning is not a singularity in the traditional sense, but rather a bounce, a collapse, followed by expansion. And in the rotating variant of this model, it's more than a bounce, it's a spin-up. The parent black hole that birthed our universe wasn't static, it was rotating, and so are we. This theory builds on the idea that a black hole can carry angular momentum. In the language of relativity, this is known as a Kerr black hole, a rotating solution to Einstein's field equations first described in 1963. Unlike a simple Schwarzschild black hole, which doesn't rotate, a Kerr black hole twists spacetime as it spins, dragging nearby matter, and even light around with it, a phenomenon called frame dragging. Now imagine that this spinning black hole doesn't just exist in isolation. Imagine that within it, a universe is forming. A universe born with rotation embedded into the very structure of its spacetime. In 2023, the James Webb Space Telescope, JWST, captured images of distant early galaxies. These galaxies, among the first to form after the Big Bang, showed something strange. A preference in rotation. Approximately 2/3 were spinning clockwise. Only 1/3 spun counterclockwise. This wasn't what we expected. In a universe formed by random processes, we'd anticipate an even split. Galaxies should rotate in both directions equally, like coins flipped by chance across the cosmos. But here was a statistical imbalance, a subtle yet significant hint that something about our universe had a preferred direction. Physicist Leor Shamir analyzed over 260 galaxies and found this discrepancy. While it has yet to be confirmed by other surveys, and some suggest selection bias may be to blame, the mere possibility has sparked renewed interest in black hole cosmology. Because if the universe was born inside a rotating black hole, then this preferred spin might not be an accident. It might be a signature embedded in the galaxies themselves. Let's zoom out both figuratively and literally. In the Kerr solution, rotation has profound effects. Not only does it alter the geometry of spacetime, but it also changes the causal structure of the black hole. Unlike non-rotating black holes, Kerr, black holes contain an inner horizon, an ergosphere, and potentially even a passage through to another region of spacetime. From a cosmological perspective, rotation provides several fascinating advantages. A rotating black hole universe generates natural anisotropy, a slight departure from perfect symmetry, just like what we observe in the cosmic microwave background, CMB. Predicts a direction of time. The spin defines an arrow, possibly linking to the thermodynamic arrow of time we experience. Offers an internal engine. The centrifugal effects of rotation can counterbalance gravitational collapse, enabling the bounce that prevents a singularity. And here's where the connection gets eerie. The mathematics of such a rotating bounce generate conditions that closely mimic cosmic inflation, the rapid expansion theorized to occur in the early universe. In the Standard Model, inflation is added to solve problems like flatness, homogeneity, and the horizon problem. But in black hole cosmology, inflation emerges naturally from the dynamics of rotation and collapse. That's not a patch, that's a prediction. If our universe is the interior of a rotating black hole, what does that make the event horizon? From our side, it's the observable edge of the universe. But from the outside, in the hypothetical parent universe, it's a black hole's outer boundary cloaking a strange interior. And if the collapse didn't end in a singularity, but instead led to a bounce, then the matter that fell inward never stopped. It rebounded outward through what's called an Einstein-Rosen bridge, a non-traversable wormhole that connects two regions of space-time. Each black hole becomes a cosmic womb, birthing a new universe. Each new universe begins with its own laws, structures, and dimensions, but perhaps carries echoes of its origin encoded in its rotation, its geometry, and its quantum state. In this framework, our universe is a child, but it, too, may become a parent. Every black hole within our cosmos could harbor another universe beyond its own event horizon. It's a fractal vision of existence, universes within universes, each one spinning, evolving, birthing new realities beyond the grasp of the last. This leads to one of the most poetic and most haunting questions in cosmology. If our universe was born from a black hole in another universe, then where did that parent universe come from? And what about its parent? Does this chain continue forever? Are we just one in a potentially infinite hierarchy of embedded realities? And if so, is there an origin, a primordial universe, a first black hole? Or is it really turtles all the way down? We don't know. And that not knowing is part of what makes this theory so beautiful, because in exploring it, we're not just asking about equations and energy, we're asking about meaning, about place, and about the strange possibility that the truest boundaries of our universe are not distant galaxies, but the curved walls of a cosmic interior. Let's add one last speculative layer. If this theory holds and black holes birth new universes, then perhaps sufficiently advanced civilizations, those that reach Type 3 on the Kardashev Scale, don't simply master energy, they master creation. They could, in theory, collapse matter in a controlled way to form artificial black holes, seeding new universes. Not as weapons, not as experiments, but as refuges. What if the solution to the Fermi Paradox, the question of why we don't see evidence of alien life, is simply this: the most advanced beings have left. They've migrated into universes of their own design, universes better suited to their existence, universes they control from the inside. And we're the ones who stayed or were born here long after the architects had gone. It's a chilling, humbling possibility, but not a hopeless one, because it means that intelligence doesn't disappear. It evolves in ways we cannot yet comprehend. In the next section, we'll compare the rotating black hole cosmology model to the standard Big Bang model and ask where each excels, where they falter, and what new light they cast on the mysteries of inflation, dark energy, and cosmic structure. But already one thing is clear: this theory doesn't just reshape how we think about black holes. It reshapes how we think about the entire universe. Maybe we were never meant to escape black holes. Maybe we were born in one. Two origins, one universe, a tale of two cosmologies. So far, we've journeyed through the core ideas behind rotating black hole cosmology, a universe born not from a single explosive point, but from a collapse, a bounce, and a spin. But before we get swept up in the poetic allure of this alternative model, we must step back and ask, how does it compare with the reigning paradigm? The standard model of cosmology built upon the Big Bang theory has withstood the test of time for nearly a century. It describes an expanding universe that emerged from a hot, dense state predicted by general relativity and supported by a wealth of observational evidence. The cosmic microwave background, CMB, the abundance of light elements, the large-scale structure of galaxies, and the redshift distance relationship discovered by Hubble. So why challenge it? What gaps remain in the Big Bang story that invite other voices, like black hole cosmology, into the conversation? Let's explore the contrasts between the two. His standard model posits a singular origin, a moment of infinite density and temperature from which everything emerged. It does not, however, explain why the Big Bang happened or what came before it. At T0, our equations break down. Time itself ceases to have meaning. It is quite literally the edge of understanding. In black hole cosmology, there is no such absolute beginning. Instead, the birth of our universe is interpreted as the interior evolution of a black hole formed in another universe. This is a bounce, not a beginning, an unfolding of compressed matter into a new cosmic arena. In this model, time doesn't start. It continues, or albeit in a radically different form. One story starts from nothing, the other from something else. One of the most successful additions to the standard model is cosmic inflation, a burst of exponential expansion in the first fraction of a second after the Big Bang. This idea explains three big puzzles. Why is the universe so flat? Why is it homogeneous across vast distances? Why do distant regions have identical temperatures even though they've never been in contact? Inflation solves these problems, but at a cost. It introduces a new energy field, a new particle, the inflaton, and parameters that must be finely tuned. By contrast, rotating black hole cosmology achieves similar results without adding new ingredients. The geometry of a rotating collapse, curved space-time under torsion, naturally produces an inflation-like expansion during the bounce. In this framework, inflation isn't added on, it's built in. That elegance is seductive, but it must still be tested. Time is perhaps the most mysterious dimension we experience. In both models, the universe expands with time, but their treatment of time's origin is different. In standard cosmology, the arrow of time, the reason events unfold in one direction, is explained through entropy. The early universe was in a low entropy state, and entropy has increased ever since. But why did it start that way? Black hole cosmology offers a different lens. If our universe is the interior of a rotating black hole, then the arrow of time might be inherited from the parent universe. The spin and structure of the parent define the orientation of causality in the child. Time has a direction, not because of chance, but because of cosmic heritage. Both models agree that the CMB is a critical test. In the standard model, the CMB is the relic radiation from the hot plasma of the early universe, cooled to 27 K today and astonishingly uniform. Tiny variations in temperature on the order of microkelvin reveal the seeds of all structure in the cosmos. Black hole cosmology interprets these variations as signatures of the bounce and rotation. For instance, subtle asymmetries in the CMB polarization could indicate a preferred spin direction inherited from the black hole that birthed our cosmos. Recent high-precision data from Planck and other missions have found anomalies, dipoles, cold spots, alignment of multipoles that don't fit neatly into standard predictions. They don't prove black hole cosmology, but they whisper that something more may be at work. In the standard model, the accelerated expansion of the universe is driven by dark energy, a mysterious component that makes up about 70% of the cosmos. We know it exists. We don't know what it is. In black hole cosmology, this acceleration is a natural consequence of being inside a rotating, growing black hole. As mass continues to fall into the parent black hole, the volume of the interior universe grows. No extra field required, just a different point of view. It's as though our cosmos is inflating from the inside, not from an exotic vacuum energy, but from the continuing infall of matter in the higher dimensional world outside. Does this mean black hole cosmology wins? No, not yet. The standard model remains unmatched in its precision and predictive power, but it leaves open doors, questions it cannot answer, patterns it cannot explain. Rotating black hole cosmology doesn't close those doors. It steps through them and finds something waiting on the other side. A universe not just expanding but evolving through cosmic inheritance. A universe not born in isolation but part of a vast, possibly eternal chain of black holes and baby universes. It's bold, it's speculative, but it just might be true. Shadows and signals. Can we prove the black hole universe? We've walked the line between two grand visions of cosmic origin, the classical Big Bang and the bold elegance of black hole cosmology. The latter reinterprets the observable universe as the interior of a vast rotating black hole, its expansion, structure, and direction shaped by inherited properties from a parent universe. And it's compelling seductively so. But science doesn't thrive on poetry alone. It breathes through evidence. So we must now confront the uncomfortable question, how do we test this? How do we distinguish between metaphysical speculation and scientific reality? How do we look for the fingerprints of a parent universe from within the walls of our own? The path forward isn't smooth, but it is navigable. In 2016, a strange idea began to circulate in gravitational wave research. LIGO, which had recently detected the collision of black holes, a triumph in itself, had also registered anomalous echoes in the aftermath of some events. These faint delayed repetitions of the initial signal sparked whispers of something exotic, perhaps quantum structure at the edge of black holes, or even evidence that what we call a black hole might be more complex. Within the black hole cosmology framework, these echoes become something more. They might be reflections from the boundary of the universe itself, a sign that our cosmic horizon isn't just a limit of our view, but a real physical edge. A membrane, a wall, If that's true, then we're not just receiving whispers from dead stars. We're hearing the rumble of our cosmic container reverberations from the curvature of a larger dimensional reality. Still, critics rightly urge caution. These echoes are weak. Controversial, not universally observed. The signal could easily be noise, and multiple follow-up studies have failed to replicate the findings consistently. But like a knock in the dark once heard, it's hard to ignore. We explored one of the most fascinating and polarizing observations from the James Webb Space Telescope, a disparity in galactic rotation. According to physicist Leor Shamir's analysis, early galaxies appear to spin with a directional bias. Roughly 2/3 rotate clockwise, and only 1/3 counterclockwise. This imbalance isn't predicted by standard cosmology. In fact, it should be impossible if the universe had no preferred direction at birth. To black hole cosmologists, this anomaly isn't an error, it's a clue. A spinning parent black hole could imprint that preferred rotation on its internal space. The distribution wouldn't need to be perfectly even. It would tilt, twist, spiral. But is this a real effect or an artifact of limited data? Shamir's study looked at a few hundred galaxies, a statistically meaningful sample, but still vulnerable to selection bias. Other surveys have not found the same asymmetry. The result, while electrifying, remains unconfirmed. It stands as a testable prediction, a challenge, and a reminder that all new theories live under the microscope of skepticism. In theoretical physics, white holes are the mirror image of black holes, regions that matter and energy can exit but never enter. In the black hole cosmology model, the Big Bang itself is reinterpreted as a white hole event, the expulsion point of matter from a black hole in a parent universe. But here's the catch: we've never seen one. There are good reasons for this. White holes, if they exist, are probably short-lived and violently unstable. Their existence requires conditions we don't see in nature. Yet if our universe really began as a white hole, shouldn't there be some leftover trace, some relic, however faint? At the moment, no such evidence has been found. The model predicts that we wouldn't be able to observe the white hole directly. It would lie before our observable time, but that doesn't make it immune to critique. Critics argue that redefining unobservable phenomena is a dangerous game. The model must make falsifiable predictions or risk drifting into the realm of unfalsifiable metaphysics. The cosmic microwave background remains one of the most powerful tools in cosmology, a picture of the infant universe frozen in time. And perhaps it holds the key to resolving this debate. If our universe spun at birth, the CMB should carry that twist. We should see anisotropies, alignments, and polarization patterns that betray rotation. Indeed, some studies of the CMB, particularly those examining the so-called axis of evil, have hinted at large-scale alignments inconsistent with a purely isotropic universe. But interpretation remains murky. Are we reading deep truths in the CMB, or playing connect the dots with cosmic randomness? New missions, better data, and sharper instruments may one day tell us. To elevate black hole cosmology from hypothesis to theory, we need clear, testable predictions that differ from the standard model, repeatable, high-precision observations that support those predictions, mathematical models that don't just explain anomalies but predict them before they're observed. Gravitational wave astronomy may be the key. Upcoming missions like LISA, set to launch in the 2030s, will detect gravitational waves with unprecedented sensitivity. If echoes persist, or if we detect waves that align with internal bounce models, black hole cosmology will step out of the shadows. Similarly, quantum computing and analog gravity experiments may allow us to simulate the boundary behavior of black holes and test the holographic principle in new ways. And finally, AI-aided pattern recognition in cosmic background data may spot what human eyes miss. Black hole cosmology is not yet confirmed, but nor is it merely fantasy. It stands at the threshold between imagination and insight, compelling, controversial, and incomplete. Like all great theories before it, it asks us not just to look harder, but to look differently. It tells us that perhaps the edge of the universe is not a horizon, but a surface, not a limit, but a membrane, not a void, but the interior of something larger. And if it is correct, the proof may be drifting toward us even now, quiet ripples in the dark, waiting to be heard. Universes and the nature of existence. In black hole cosmology, our universe is not a standalone creation. It is the interior of a rotating black hole formed in another universe, a daughter universe, so to speak. This black hole collapsed under its own gravity, compressed matter and energy to extraordinary densities, and then, through mechanisms like torsion or quantum effects, triggered a bounce. That bounce didn't return to the parent universe. It unfolded inward, creating a new expanding space-time. And we live in that inward unfolding. But it doesn't end there. Just as our universe was born from a black hole, the theory suggests that black holes within our universe may do the same. Each one, if the conditions are right, may give rise to its own universe, hidden behind its event horizon, its contents forever inaccessible from our side. The result is a fractal cosmology, a universe of universes, a cosmic matryoshka doll of reality, each layer embedded in the last, each with its own physics constants and potential for complexity. This idea echoes ancient myths, the world upon the back of a turtle, standing on another turtle, and so on all the way down. But in this modern reimagining, the turtles are black holes, and they might go all the way up too. Inevitably, we're drawn to ask, where did it all begin? If our universe was born from a parent black hole, where did that parent universe come from? Was it born from yet another black hole, and that one, and that one? Does the chain go back forever? This is the cosmic equivalent of the chicken and egg problem raised to infinite dimensions. In one view, there is no first universe, just an eternal lineage of cosmic births and rebirths governed not by divine intervention or absolute beginnings, but by recurring physical processes. But in another possibility, there was a first, a primordial pavement universe, the originator of all others. Perhaps this universe didn't form from a black hole. Perhaps it formed black holes that gave rise to others. It might have been vastly simpler or incomprehensibly complex. Or maybe, just maybe, it was created on purpose. Some theorists, including futurist thinkers like John Michael Godier, have explored the notion that sufficiently advanced civilizations might gain the ability to engineer black holes and thus create universes. Think about that. If civilizations could control the parameters of these artificial black holes, mass rotation charge, they might influence the initial conditions of the resulting universe. They could, in theory, design universes optimized for stability, complexity, or even life. Like gardeners planting new gardens not on planets, but across space-time itself. And if that's the case, our universe might not just be a child. It might be an engineered offspring, tailored, fine-tuned, and set spinning by hands or minds we cannot yet imagine. This possibility reframes everything. It suggests that the fine-tuning we observe in the laws of physics, the precise values of fundamental constants that make atoms, chemistry, stars, and life possible, might not be a coincidence or a mystery. It might be a legacy. we might exist because someone or something intended us to. If so, where are they? Where are the architects, the creators, the advanced civilizations that supposedly seeded the black hole from which our universe bloomed? One answer is chilling in its logic: they've moved on. Once a civilization attains the ability to create its own universe, its own ideal cosmos, why remain in this one? Why not construct a new universe with more favorable physics, richer energy, states, fewer limits? Why not enter the very black hole they create, migrating to a realm of their own design? This becomes a potential answer to the Fermi Paradox, the riddle of why we see no evidence of alien civilizations. Perhaps the most advanced beings don't leave artifacts, they leave the universe. And in their place we find silence. But not emptiness, because in that silence, life begins again. For all its physics, black hole cosmology evokes a sense of something greater. It doesn't demand belief in a god or an afterlife or a soul, but it does whisper that our universe is not alone, and neither are we. It suggests that consciousness may not be a fluke, but a pattern, an emergent behavior that arises in many universes across many horizons. It invites us to see ourselves not as cosmic accidents, but as cosmic descendants born of a long lineage of realities, each giving birth to the next, not unlike life itself. In this model, death is not an end. Collapse is not defeat. Every black hole is a potential beginning, every boundary a doorway. If black hole cosmology is true, we live inside a structure far larger, older, and more dynamic than we've ever imagined. But even if it is not, if future experiments disprove it, we've still gained something precious. We've learned that the universe is open to imagination, but tethered by reason, that it invites questions even when it withholds answers, and that every time we think we've reached the edge of knowledge, we find not a wall, but a mirror reflecting our own desire to understand. Never assume the sky is the limit. The edge of the universe might just be the start of another. And if it is, then the most human thing we can do is to keep wondering what comes next.